Мы, кажется, уже запустили трансляцию в Zoom, так что можно уже, наверное, начинать.
Okay. So thank you for your patience and for your interest. Today I want to speak about counting of closed hyperbolic geodesics performed by Mariam Mirzahani. And I start slowly, so since in the last lecture I had flat surfaces, I have to slowly switch to hyperbolic surfaces. So any smooth orientable surface of genus at least 2 admits a metric of constant negative curvature. Usually we use negative curvature minus 1, called hyperbolic metric. And if you allow to your hyperbolic metric to have several cusps, then one can construct hyperbolic metrics also on a sphere and on a torus. So on the left picture, you see a sphere with 6 cusps. And on the right picture, you see one punctured torus where you have your cusp at the puncture. So now I want to consider curves on surfaces, and a smooth closed curve on a surface is called simple if it does not have self-intersections. So my curves are always smooth, will never have self-intersections. And now suppose that I introduce hyperbolic metric on my topological surface. So initially I had a topological simple closed curve, and in the presence of hyperbolic metric, if I let my curve contract, so suppose that we put some oil on our surface and our initial curve is made from some elastic cord, then this cord will progressively contract to a geodesic, which is normal. And it is not a complicated theorem to prove that if the initial curve didn't have self-intersections, then the resulting geodesic would not have some self-intersections. So from now on, I will always consider only essential simple closed curves, the ones which do not bound a disk and which do not go around a single cusp, because I want to get an interesting geodesic after contraction. So if we have an elastic geodesic which goes around the circle, around the disk, it will contract to a point, and if it encircles a cusp, it will shrink and escape in the cusp. So here we have a curve which has several cusps on one side and 3 cusps on one side, 3 cusps on the other side. So it would contract to something interesting, and yet non-self-intersecting. So, and again, sorry, at this seminar, probably it would be exaggeration, but I would like, so in this seminar, usually one considers the moduli space of complex curves as moduli space of complex curves. But by uniformization theorem, to every complex curve with marked points, you can associate a hyperbolic surface. So for example, at this particular picture, I have 4 punctured CP1, and there is a unique hyperbolic metric which corresponds to this 4 punctured CP1, where I have cusps at the punctures. And when I can send 3 points out of 4 on CP1 to 0, 1, and infinity, and the 4th point is a free parameter. So the configuration space of 4 punctured CP1s is just 3 punctured sphere. So similarly, and the 4th point, since I have 4, when I move the 4th point is a free parameter. And when I move this 4th point, my hyperbolic metric changes. So here, when I make one point approach to another point, my hyperbolic surface gets sort of a bottleneck. And the 2 complex parameters, which you easily see on the left picture in terms of complex curves, can be also easily seen on the right picture. Not as complex.
Sorry, Anton.
Yeah.
What do you mean by 2 complex parameters?
Sorry, one complex parameter on the left picture is become 2 real parameters on the right picture, and these 2 real parameters on the right picture you do not see complex structure right away. But on the right picture, you still see that the surface, this hyperbolic metric, you can easily see that it's parameterized by two real parameters. And as real parameters, you can choose the length of the geodesic, which goes exactly at this bottleneck. And also, well, I was lazy. I draw a picture in such a way that one have an impression that all four cusps live sort of in the same plane. But it's clear that if you chop your surface by this bottleneck, you can twist one part with respect to another by any twist. And this twist is the second real parameter. And actually, they have interest, well, they're quite meaningful, and the generalization of these two parameters are called Fenchel-Nielsen coordinates. But anyway, at that point, the only thing which I need is that we get a rich, interesting family of, in one language, complex structures for surfaces of given topology, so of given genus G and fixed number n of mark points, or in terms of hyperbolic metrics, a rich family, smooth family, or even complex family of hyperbolic metrics on the surface of fixed topology. Now, I'm interested not in the moduli space, I'm interested in multicurves, and let me describe the family of multicurves. So to tell a bit more about multicurves, first I would like to arrange them into huge classes. And I will say that two simple closed curves on a smooth surface have the same topological type if there is a diffeomorphism of the surface, which sends one curve to another. When they are mark points, usually we assume that mark points are numbered and our diffeomorphisms are supposed to preserve the numbering. It immediately follows from classification theorem of surfaces that there is a finite number of topological types of simple closed curves. So, for example, if surface doesn't have punctures at all, then all simple closed curves which do not separate the surface into two pieces belong to the same class. And if they do separate the surface into two pieces, then it's the genus of each piece which characterizes the topological type. Now, one can consider slightly more general objects. One can consider primitive multicurves, that is, collections of pairwise disjoint, non-homotopic simple closed curves. So I insist all my curves in this lecture are always closed, and there are no intersections, never, neither self-intersections nor intersections between different curves. For any fixed pair, genus, and number of punctures, the number of topological types of primitive multicurves on the surface of genus G with n punctures is also finite. And here's an example for genus 2 and no punctures. So this is just surfaces of genus G. So G is equal to 2, n is equal to 0. And I claim that if you have a primitive simple closed multicurve, then by diffeomorphism, you can bring it to one of these 6 cases. And I suggest to slow down here a little bit and to make an exercise, because our intuition is somehow a little bit biased by having to work with homology. And I insist that here we do not work with homology. For example, their middle, so this curve on the surface, which is on the left bottom corner, is clearly homologous to 0. So from the point of homology, it is just 0 cycle. Now, as an exercise, we can probably do the following thing. Take the surface on the bottom right picture and erase, for example, the rightmost circle. I claim that the resulting multicurve, which now has 2 components, is already presented on the picture. So by diffeomorphism, you can bring it to one of the multicurves which are presented on the picture. And since there are 2 components, it should be one of the multi-curves in the middle row. So do you agree that it would be one which...
You mean in the middle column?
Or in the middle column, sorry. Yes, so either this one or that one, just because there are two components. So do we agree that we'll get this one? Basically, the argument, if you chop, so this we just forgot, so this curve is forgotten. This one and that one, they're still there. But if I chop my surface by these two curves, I still get something connected. So in this case, if I chop my surface by two circles, I get something connected. In this case, I will get two connected components. So if you believe in my statement, then it should be the resulting multi-curve should be in the same class as this one. And this somehow shows that these classes, these topological classes, they're quite large. So we have very different multi-curves in the same class. And another comment is that actually you can recognize in these pictures boundary classes of the moduli space M2. If you shrink the resulting curves to a node, then you will get stable curves. And here I presented a complete list of possible types of stable curves. Okay, so that's my topological classes of primitive multi-curves on the surface of genus 2. And now, instead of working with all diffeomorphisms, it's often more convenient to work with a mapping class group, which is the group of all diffeomorphisms of a closed, smooth, orientable surface, quotient over diffeomorphisms which are homotopic to identity. And by convention, as I already mentioned, when our surface has marked points, we require that diffeomorphisms send marked points to marked points, respecting the ordering. Okay, so now this is a much more realistic picture of a multi-curve. And this time I do not assume that it is primitive or reduced or whatever. Basically, I just draw a complicated collection of closed lines on the surface. And the only requirement is that they do not have self-intersections. They do not have mutual intersections, and that there are no components which are homotopic to freely homotopic to a point. And so the claim that there is only finite number of topological types of primitive multi-curves can be translated in the following way. So if you apply an appropriate diffeomorphism to this surface and to this curve, rather, then you can unwrap it to something which basically corresponds to one of the 6 pictures which was on the previous slide, except that now I do not forbid homotopic components, but I will encode them in the following way. So if unwrapped if unwrapped curve looks like here, then I will say, I will memorize these 3 homotopic components just as a weight of a representative of them. Similarly, here I have 2 homotopic components. I memorize them just as weight 2 of a representative of them. So this is, now this picture represents a true multi-curve as you can imagine it. This picture represents its sort of simplified representative, so it's topological class. And the picture on the right represents the associated reduced multi-curve, where you forget about weights. You just replace all the weights by 1. The previous picture, the picture on the picture on this slide gave description of all possible primitive multicurves. Now, if you take the components, when there are several connected components with integer positive weights, sorry?
Any questions?
Apparently it was an excellent. So if you take components with positive integer weights, then you get topological classes of general topological classes of multicurves. Oops, sorry, I moved in the wrong direction. And to finish with this slide, why well, it's not me who introduced multicurves, of course. So the multicurves and the space of multicurves was introduced, up to best of my knowledge, by Bill Thurston. And one needs multicurves in certain situations. When we work with curves, we often, especially with closed curves, we often use first homology. Now, we cannot use first homology always, because I want to keep track of components like here, this waist curve of my surface of genus 2. And from the point of view of the first homology, this is just a zero cycle. First homology does not see it. Second, I cannot use fundamental.
Anton,
yes?
You may address a question in chat.
Oops, I am in full screen and I have not seen it, sorry. Yes. Reduced multicurve and primitive multicurve are the same. Absolutely. I apologize. So in literature, some people use one notion, some people use another. For me, they're the same. And actually, I do not know which one is, whether there is any preference, even in frequency. The last thing which I wanted to say is that also when one works with closed curves, one can use fundamental group. But fundamental group is mostly designed to work with curves which are allowed to have self-intersections. It has many advantages, but in this particular context, when we work with curves which do not have self-intersections, this notion of multicurve is often useful. And they also have beautiful structure, as we'll see shortly. And one of the reasons why multicurves are useful is that since they do not have self-intersections, it's particularly convenient to cut our surface along multicurves into simpler components. And that's why it's sort of a natural ingredient for various recursions. Okay, now this is a symbolic picture of a space of multicurves. Right now, I do not explain where the structure comes from, but in certain, one can introduce certain, so right now I ask you to believe me just without any serious justification. I hope to give certain justification at the end of this lecture. So if I will have time. But in certain natural piecewise linear coordinates, integral multicurves like integral homology cycles are represented by lattice points in a vector space. So here I try to illustrate distinct orbits of the mapping class group. So points in red are schematically represent multicurves which correspond to, for which the underlying reduced or primitive multicurve corresponds to one topological type, and blue points represent those for which, when you forget about weights and replace the weights by one, you get another topological class. So, for example, for surface of genus 6, if I would use this convention, I would be supposed to get 6 different colors corresponding to our 6 types. And these integral points are sort of nicely distributed in this space. So we have this piecewise linear structure, and our mapping class group acts by piecewise linear transformations on this conical polytope. Now, in the presence of hyperbolic metric, the integral multicurves take the shape of simple closed geodesic multicurves, and actually, what I'm hiding and what I would not discuss is that any, not necessarily integral, point of this conical polytope defines a measured geodesic lamination. So, and again, jumping a bit ahead, these natural coordinates which I mentioned are, for example, the train track coordinates. So I hope to arrive to them. Now, what I need is that our so we have piecewise linear structure and sort of equivalent of integral points. So this allows us to define a measure on our polytope, and the mapping class group preserves this measure. So the theorem which I would need, and which would be sort of probably a little bit hidden in the whole story, but which is important for the story, is that the action of the mapping class group on this polytope is ergodic with respect to the Lebesgue measure class. So any measurable subset which is invariant on the mapping class group has measure 0, or its complement has measure 0. And any measure which is invariant under the action of the mapping class group is proportional to Thurston measure. So this theorem of Mézur will be used shortly. And now I'm finally arriving to Mirzahani's count of simple closed hyperbolic geodesics. So the bald-headed person on the right in this picture is Greg McShane, and the picture is taken by François Labourie at CERN. So here's the counting story. So I'm coming back to a picture of a multi-curve on the surface. And right at this stage, it's just topological surface and topological multi-curve. Now I introduced some hyperbolic metric. I choose just any hyperbolic metric on the surface, and I let my curves contract. We already discussed that every curve contracts to a simple closed geodesic, which doesn't have self-intersections. One can extend the theorem which I mentioned, and also relatively easily prove that if initial topological curves do not intersect between each other, then their geodesic representatives would not intersect neither. So this is just to justify the simplicity of my pictures.
Anton,
yes?
Whether there is some flow that contracts a simple curve into the corresponding simple geodesic?
Flow in which space?
One parameter family of one parameter group.
Oh, I see. So you are asking, is there a natural family of continuous deformation which?
Yeah, exactly.
I think so. Yeah. I'm almost here. I think so. I think you can define it relatively easily.
Okay.
basically, so here's the proof. Just imagine that these curves are, so this is sort of Arnold's style proof. Imagine that that's elastic cords. They would contract, maybe as in the proof of Poincare theorem, you have to take care of avoiding some singularities during these contractions. But in this case, I think that everything is easier, and right away, I cannot imagine situation when singularities can appear. The curvature of the, no, I think that the curve would be simpler and simpler in a sense. So this situation is, to me, seems way simpler than.
Yeah, but still, you do not assert that you can write down this flow. You just
since it has sort of simple-minded physical meaning, so it should satisfy sort of very natural and sort of elementary equations to my mind.
Okay, sorry for interrupting.
No, I agree. This is a natural question, and surprisingly, I agree. I've never seen this equations written down, but I think that it should not be complicated, and most likely they were written down many times. At least this is my expectation. Okay, now, since my topological simple closed curve contracted in the present, so from now on, I'm choosing some hyperbolic metric, and it would be a parameter, but for a while, it would be fixed. So in the presence of a fixed hyperbolic metric, all my curves constructed to simple closed geodesics, I can measure their length. And in this way, I can associate a length to the initial multi-curve. Just saying that if I have a multi-curve with certain integer weights AI, I replace it by a primitive or this multi-curve where there are no weights. I let it contract. I measure the length of corresponding geodesic components, and then I recall that I had weights, and I take linear combination of length of components, which incorporates the weights. And in this way, in the presence of hyperbolic metric X, I associate to my multi-curve gamma a length. And now, since I can bound the length, I can count multi-curves. Namely, I will denote by Sx, where X is hyperbolic metric, L gamma, the number of simple closed geodesic multi-curves on my hyperbolic surface X of topological type gamma and of hyperbolic length at most L. There is finite number of them. When I make L grow, this number grows, and the result of Mirzahani counts the asymptotic growth of this number of simple closed geodesic multi-curves in metric X of length at most L, where L is supposed to be, well, to be very large. So the theorem of Mirzahani claims that this growth rate is polynomial in L. Recall that if you count the number of all closed geodesics, then the number of all closed geodesics grows exponentially in L. So it's e to the L divided by L. Here, the constraint that our geodesic does not have right to self-intersect reduces the number of geodesics considerably from exponential growth to polynomial growth. So that they're sort of rare. There are not so many of them. If you take a closed geodesic by random, a long closed geodesic by random, it will have tons of self-intersections. So here we count very special closed geodesics, this simple closed geodesics. So the growth rate is exponential. Oh, sorry, it's polynomial, where the power is 6g minus 6 plus n, plus 2n, so it depends only on genus and n. And now what is particularly interesting in this story is the structure of the coefficient in this polynomial growth rate. So the coefficient can be split into two parts, where one part depends only on hyperbolic metric and doesn't know anything about topological type of multicurve. So it's one and the same coefficient for all topological types of multicurves. So you can, for example, you can count simple closed curves, and they can be separating or non-separating. For both topological types, the growth rate is polynomial with the same power, but the coefficient would be different. So there are more ones than the others. And however, in this coefficient, then there is this part which depends only on hyperbolic metric, would be shared by both separating and non-separating. And there would be part of this coefficient, the C of gamma, which doesn't know anything about hyperbolic metric and knows whether gamma is separating topological type or non-separating topological type. And by certain reasons, so in Mirzahani distinguishes a global constant BGN, which depends only on genus and n, and which has certain topological meaning. So actually, this BGN is just the average of this first coefficient with respect to the entire moduli space. Now, I have to explain what is so astonishing in this structure of the coefficient.
Anton,
yes.
Why are you speaking about rational multicurve rather than integer one?
Because I stupidly copied the statement directly from the paper of Mirzahani.
So it should be the integer.
It should be, so for my purposes, it should be integer, but actually there is almost no difference between defining integer and rational. They can be defined analogously, but for my purposes, forget about rational, I work with integral multicurves. Yes.
Serежа, at least there was some reason for making it rational. When we consider some limits, like projective limits and so on, then we just scale it by
yes, that's
factor.
what I understand, but I'm asking about Anton's talk.
So in my talk, I don't need rational weights. And in the original theorem of Mirzahani, she proves the theorem for rational weights. There is no big, so in everything which I will mention, there is basically no difference. Now my pathetic admiration of the coefficient should be justified. So suppose that we're counting two topological types, as in my example, for example, separating and non-separating simple closed geodesics. And we can count both, and we can take a ratio, and we can pass to a limit when limit tends to infinity. This structure of coefficient shows that if you take the ratio and pass to the limit when L tends to infinity, that the only thing which survives is this C of gamma 1 in numerator and C of gamma 2 in denominator. And it implies that to count simple closed geodesics, or more generally, to count multicurves, we used some hyperbolic metric x. But when we count frequencies, so in this limit at the bottom of the page, there are no traces of hyperbolic metric, it disappeared. So it was used, so it was sort of auxiliary construction which we used to introduce counting function. But at the end of the story, it disappears, meaning that frequencies are the same whatever hyperbolic metric in enormous class of hyperbolic metrics you consider. And this is somehow surprising, at least at the first glance, because when you fix just the genus of the surface G and the number of cusps, you can create an enormous variety of hyperbolic surfaces. And in particular, you can create hyperbolic surfaces which are very peculiar. For example, you can consider some covers over surfaces of smaller genus and so on. You can consider surfaces having very long and very narrow hyperbolic bottlenecks and so on. And despite the fact that the structure of hyperbolic surface can be very different within given genus and given number of points, the frequencies of topological types of multicurves are the same. They do not see, at the end of the story, they do not see hyperbolic metric. For example, one of the examples which was calculated directly in the paper of Mirzahani is this six-punctured sphere, as one which was presented at one of the first slides. And for six-punctured sphere, a simple closed geodesic can have either 3 cusps on both sides or 2 cusps and 4 cusps. And you can count how often do you see the ones and the others, meaning that you consider all simple closed geodesics of length at most 1 milliard. There is finite number of them. It's 1 milliard power, which was showed in the previous slide. So you count both of them, you divide one of the over the other, and you let 1 milliard tend to infinity. And what you get is 4/3. So the theorem of Mirzahani is not existence theorem. She gave explicit formula for her C of gamma, and they expressed in terms of Witten-Concevic correlators. And these frequencies are rational numbers, which are explicitly computable. So these 4/3 were computed in the original paper of Mirzahani. They were confirmed by experiments of Mark Bell, and later by other computer experiments and comparison with other stories. And this 4/3 is absolutely correct. So, and now I come back to my square tile surfaces. I already told at the previous lecture that I am obsessed by square tile surfaces.
And what are the values of C of gamma 1 and C of gamma 2 in the previous situation? Here is the quotient, but do we know what are the values separately?
Yes, I do not dare to tell them by heart. I have to look at the note, because so there are intersection numbers which are involved, and there are also combinatorial constants which are involved. And without looking at the reliable source, I do not dare to tell them by heart.
Probably so you remember whether they are rational or not.
Oh, yes. Yes, of course. All of them are rational. So the structure of C of gamma is as follows. It's some combinatorial constant, which, so so this C of gammas are, oh, wait a bit. It depends, okay. It depends whether you can whether you count primitive multicurves or non-primitive multicurves. So if you consider primitive multicurves, then the structure is as follows. It's some combinatorial constant, so basically some factorials and such, and polynomial in intersection numbers, which are all rational. Now, if you count non-primitive multicurves, all of them with all weights, then you have to sum up with respect to the weights, and this summation with respect to all possible weights provides you with extra factor, and this extra factor is product of values of zeta function at integer, at even integers. And conjecturally, oh, not even conjecturally. So here we know that it's pi to appropriate power. So arithmetically, you get a rational number times pi power dimension of the corresponding space.
Okay, thanks.
But everything is somehow clearly and explicitly described by Mirzahani in the original paper. So it's perfectly known. And now I arrive to my square tile surfaces. I already mentioned at the first lecture that when you have a square tile surface like on the right, you can associate to it a topological surface as on the left, just marking all corners with the angle pi, this one, that one, that one, that one, that one, and these two. So they're here. And also drawing the waist curve of all horizontal waist curves of cylinders. So here the maximal cylinders are colored in this dark gray here, light gray here, and then there are two maximal cylinders here on the left and on the right. For me, maximal cylinders are flat cylinders which are obtained by withdrawing from the surface all singular horizontal leaves. When I withdraw all singular horizontal leaves, my surface decomposes into a finite collection of cylinders. So for each cylinder, I take the waist curve, which is in red, and I get a multi-curve. So I can even memorize the information about the heights of the cylinders. So for me, height is vertical. So this cylinder, sort of relatively dark gray, has height 2. This cylinder, height 1. This also height 1. And this cylinder in the bottom, which is the darkest, has height 2, because there are two parallel bands of squares which I use to glue the cylinder. And I can use this data, I can encode this data by associating weights to the components of my multi-curve. So the multi-curve associated to this particular square tile surface is on the left picture. It's 2 gamma 1 because the corresponding cylinder is glued from two horizontal bands of squares. Gamma 2 here, gamma 3, and here again 2 gamma 4 because it's not one band but two bands of two horizontal bands of squares. And now, so at the first lecture, we're counting square tile surfaces. So at this lecture, we're counting multi-curves, and we can compute frequencies of multi-curves, but also we can compute frequencies of square tile surfaces corresponding to these particular multi-curves. So here's a theorem. Yes?
Sorry, I'm not quite sure. I understand how you see the multiplicity of a geodesic on the right picture.
Mm-hmm. On the right picture, so we first decompose the surface into cylinders. Just a second. So when I have a square tile surface, it's decomposed into cylinders. For example, I have this cylinder.
Yeah.
I count how many bands. I don't know. What do you see?
Yeah, we see this perfectly.
Okay, so I have one band here, then one more band here, one more band of squares here, one more here. So I just count the number of horizontal bands which I use. So the height of the cylinder.
Okay.
It is so on what you see on the screen. The bottom cylinder is colored in dark gray, and there is one band of squares beyond this red line and another band of squares above this red line. And that's why the height of the cylinder for me is so it's actually this height, the distance between these two singular layers, the vertical distance between these two singular layers, and it is 2.
So it's just a measure.
Yes.
Yeah, I see. And this is just the length of the segment.
Yes.
The length of the vertical segment.
Yes. Or
Right.
if you wish, if you consider
Great, it's enough. Yeah.
the height function, it's the distance between the critical levels.
Okay.
So the theorem says that the frequency of multi-curves computed using hyperbolic metric and the frequency of square-tiled surfaces associated to this multi-curve is the same. So whatever genus G, number of points n in topological type gamma you choose, you can compute frequency of corresponding multi-curves among all multi-curves and frequency of corresponding square-tiled surfaces among all square-tiled surfaces. These frequencies are the same. It's not asymptotic result, it's for any genus, for small genus, for small number of points, whatever, and for any topological class of gamma. We proved it sort of by formulas, and there is a more geometric proof due to Francisco Arana Herrera, who used Mirzahani's earthquake flow.
Yeah, and there is one more question in chat.
Oops, sorry. Yeah, I thank you for attracting my attention. So the question is, do we construct the square-tiled surface using the formal sum of multi-curves? I suggest to see it differently. So to every square-tiled surface, we can associate a multi-curve with weights. And then among all square-tiled surfaces, I consider only square-tiled surfaces which correspond to the pre-images of this multi-curve. And to define frequencies, I just consider square-tiled surfaces tiled with at most milliard squares. Then for every topological type, I obtain certain subset of square-tiled surfaces. And then to define these frequencies, I let the bound for the number of squares which I used to construct the tiling to infinity. So say, well, it can be done better and more constructively, but I think that the better structure is not the multi-curve, but the dual graph to it, the stable graph. The stable graph really shows how to physically construct the square-tiled surface. And now I can finally define what is a random multi-curve for me. So we have seen that to define these frequencies, we use some hyperbolic metric, which provides us with a bound for the length. But when we choose so basically the space of integral multicurves does not depend on hyperbolic metric. But to chop this infinite polyhedral cone, saying that we consider only multicurves of length at most million, we have to introduce some hyperbolic metric for which the length would be at most million. If we use some other hyperbolic metric, then it would chop some other finite part of our polyhedral cone. But basically the frequencies, it's purely auction. So it's, we use this metric only temporarily. We could use any other reasonable way to exhaust our polyhedral cone, and the sets of blue points and red points are already defined. So their frequencies are defined no matter what hyperbolic metric or what other reasonable way to exhaust our space we use. And so this is informal explanation why frequencies do not depend on hyperbolic metric. Now, more formally, the proof of Mirzahani works like this. So recall that this Sx L gamma is our counting function, which counts multicurves of topological type gamma, having length at most L with respect to hyperbolic metric x. And by definition, the frequency is the limit of this counting function over L power 6g minus 6 plus 2n. Now, if we want to compute this limit, it is by definition the same as to compute the following thing. So here I have the same denominator, and in numerator I just used sort of extended definition of this counting function. We take a unit ball, so there everything of length at most 1. We scale it by factor L, so now we have objects of length at most L, and we take the orbit of our multicurve gamma, and we look at all the points of this orbit which get inside of this sort of ball of radius L. And then we pass to the limit like this. Now, we can declare that this is a Mirzahani measure mu gamma of this ball. And by ergodic theorem, if in terms of the previous picture, we define the measure using only red points instead of using both red and blue points. Since both red points and blue points are invariant under the mapping class group, we'll get invariant measure. And by ergodic theorem, this measure would be constant proportional to the measure which comes from counting all points. So basically, the entire computation is computation of this k gamma. We have to prove that it's non-zero. And computation of this k gamma goes like this. So we integrate everything, so following Mirzahani, so she integrates everything with respect to the moduli space. So, and unwraps the definition. So
the problem is it's difficult to integrate over a non-compact space.
Yes. So the true problem is this equality, because basically in this equality, she interchanges the integration with respect to non-compact space and the limit. And this is a dangerous operation. And here she uses a non-trivial estimate, which she thoroughly elaborates, saying that, so it's at the bottom of the slide, saying that for any L, the ratio of our counting function over L power 6g minus 6 plus 2n, which we use in the limit, is bounded by some integrable function. So this is a non-trivial result in hyperbolic geometry, which she works on quite seriously. And this result justifies the interchange of this equality and the limit. As soon as it is interchanged, everything becomes easier again, because now this limit is by definition the limit which is here, and then he uses another result that in the average she gets a polynomial in L, which is expressed in terms of intersection numbers. And that's, so basically the entire proof is combination of common sense, ergodicity theorem of Mézur, and this highly non-trivial interchange of passing to the limit and integration with respect to the entire modeling space. Okay, and now the most complicated technical part of the story is over, and I arrived to funnies, and the funnies are as follows. So we have Mirzahani's formula for frequencies of various types, topological types of multi-curves. So we now have the answers for all topological types. So since we already have answers, it's natural to ask questions. And the questions are, so what does it give? Which simple closed geodesics are more frequent, for example, separating or non-separating? And also you take a random non-primitive multi-curve, random in the sense that you establish your bound, you chop a finite piece of your polyhedral cone, you have now finite number of points there, you take random point. So what is the structure of the corresponding multi-curve? Is the underlying reduced curve separating or not? How many components does it have? So all kind of questions. So what can be said about a random multi-curve like on the picture? For example, we can consider sort of conditional probability. Just compare separating and non-separating simple closed curves in genus 2. In the original paper of Mirzahani, she computes the frequency and she gets 1/6. So if you correct a tiny bug, so she puts at some point factor of 2 in numerator instead of denominator, you get 1/24. You correct another tiny bug, you get 1/48. I should say that we were extremely nervous when we got this 1/48 instead of 1/6. By now, it is. So I asked all friends and colleagues to check the answer, and because it was supposed to be the same. I told that frequencies of square tile surfaces are supposed to be, by our theorem, the same as frequencies of multi-curves. So it's 1/48. And I should say that one should not blame Mariam for not computing it correctly. It's rather surprising that it took quite a while to see that there is some incoherence. She computed everything by pure calculation. She had no cross-checks with databases, experiments, and so on. So we had much more data.
Anton,
yeah.
It looks suspicious that the sum of numerator and denominator is 49.
Why?
So you should put on the denominator probably the portion of all possible geodesics.
I'm not saying. Okay, so here I take just number of separating over number of non-separating. The ratio can be any.
So among all...
I'm not computing probability in this particular formula.
So there are some other... No. So you take all possible closed geodesics and 1/49 part of these geodesics is separating and 48/49 portion is non-separating.
Yes.
Okay.
So if you want to interpretation probabilistic, then the numbers would be like this. Yes. And now you're right. So probably I had to, I wrote it following the way Mirzahani wrote, and here that's already probabilities. So if you sum up all these numbers, you will get 1. So there's 6. And I'm saying that, yeah. So now that's already the probabilities. And that's the complete picture and what happens in genus 2. You know what is the probability of every multi-curve. The trouble is that in genus 3, there are already 41 types of multi-curves. In genus 4, there are already 378 multi-curves. In genus 5, there is 4,500, and the number grows exponentially when genus grows. And it becomes pointless to just make tables like this. So when you have a table of 5,000 cases and exact probabilities, so it's not very informative. So very natural question, which classes are more probable, which ones dry up? So what one is supposed to expect when genus is large? And to compare it with other random objects, let's consider, for example, random integer numbers. So of course, there is not such a thing as a random integer. You have to take a large interval 1 over n, then take randomly with the same probability an integer in this interval, and you can ask about its arithmetic properties. Arithmetic properties, mostly it's decomposition, the prime decomposition. So you compose it into a product of primes and ask what are the properties of this decomposition. So this question was studied by number theorists since quite a while. And a classical theorem in this story is Erdős-Kacs theorem. So, well, probably the most classical story is the prime number theorem. What is the probability that the number would be prime on the nodes? The probability is log n over n. But then you can consider more complicated decompositions. And for example, you can ask how many prime factors do you have without counting multiplicity. So I do not care about these weights m1, etc., and k. I count only the number of prime factors. So the Erdős-Kacs theorem says that the centered and rescale distribution of the counting function omega tends to normal distribution, where you see the mean and the variance. So there are really not so many factors, and they were further results of Selberg, Renyi, and Turan describing rate of convergence. So this is random integer numbers. Now one can study random permutations. Take a random permutation of n elements, decompose it into a product of disjoint cycles, and one can discuss what is the number of cycles typically in a permutation. So what is the number of cycles in a random permutation? The theorem of Goncharov, and not Sasha Goncharov, it's much older theorem, says that again, if you rescale, normalize the distribution, you get normal distribution, and the mean value of number of cycles of random permutation is log n, and this is the correctional term. Gamma is Euler gamma, and the variance is also log n with slightly different correction term. So now let's come back to square-tiled surfaces and to multi-curves. I'm discussing them simultaneously because we have seen that the frequencies are the same. And the questions can be the following. So for example, how many singular horizontal leaves in blue on the right picture has a random square-tiled surface of genus G? Or what is the probability distribution for the number of maximal horizontal cylinders, which are in red on the left picture? What is the typical heights of the cylinders? Or in terms of multi-curve, what are the typical weights of a multi-curve? And more generally, what is the shape of a random square-tiled surface of like genus or a random multi-curve? And here is, well, it's not the answer, it's just a reminder that frequencies are the same, so the probability distributions for the number of components of a multi-curve and number of maximal horizontal cylinders are exactly the same. It's not asymptotic in large genus, it's for any genus on any n. But now I'm coming back to large genus, and here's the answer. With probability which tends to 1, the reduced multi-curve associated to a random integral multi-curve does not separate the surface. In terms of the stable graph, it means that if you take by random a multi-curve and look at the corresponding stable graph, it has a single vertex and a certain amount of loops. Now, what is the amount of loops? What is the number of components of this reduced multi-curve? It's roughly log g over 2. Non-roughly, with probability, which again tends to 1 with this speed of convergence when genus tends to infinity, the number of components of a primitive multi-curve associated to a random curve, so this number k here, would be bounded between this 0.09 of log g and 0.62 log g. The estimates are not sharp, so it would be even shorter. Now, this is interpretation in terms of multi-curves. What does it mean in terms of square-tailed surfaces? Actually, in terms of square-tailed surfaces, the fact that the associated multi-curve does not separate the surface means that all critical points would sit on the very same layer. And please forgive me, I forgot to tell important thing. To simplify the story, you see, I'm now considering only one parameter, the genus G, which tends to infinity. I assume that there are no cusps, as on the picture. I assume that there are no corners of our square-tailed surface with cone angle pi. So in terms of associated quadratic differential, I consider only holomorphic quadratic differentials. So no marked points on the surface. So all conical points of my square-tailed surface sit at the very same horizontal layer and on the very same vertical layer. So it's sort of opposite to Morse theory. There's a single critical layer, horizontal and vertical. Now, what about the heights? If you consider sort of conditional probability, if you consider only square-tailed surfaces with given number of cylinders, say 1 cylinder or 2 cylinders or 3, and you ignore all the other ones, then for square-tailed surfaces with fixed number of cylinders, all the heights would be equal to 1 with probability which tends to 1 when genus grows. If you consider all square-tailed surfaces, then it's not true anymore, and all heights would be equal to 1 with probability which tends to square root of 2 over 2. And all heights, or equivalently all weights m1, etc., mk over random multi-curve, they would be bounded by an integer m with probability square root of m over m plus 1. However, if you take a mean value of all of the sum of the weights, it's infinite in any genus. So typically they are not large, but still the mean value is infinite. It happens in probability. And now one more statement, to formulate one more statement, I can redefine random permutations. I will tune up a little bit the measure, and instead of taking permutations with uniform measure, I will choose them with slightly different measure. So once again, I will decompose my permutation into cycles. and I will associate, so I define sequence of numbers like this. And when I have a permutation with this cyclic decomposition, I associate to it a weight, which is defined using the length of cycles. The number of cycles of length 1, 2, and so on. And then to renormalize, I take the sum of all the weights, and in this way, I associate probability to every permutation. So basically, it's almost Evans measure with parameter 1/2, except that I have enumerated here zeta of 2k. When k is large, zeta of 2k is basically 1. This somehow privileges permutations with long cycles and gives some disadvantage to permutations with short cycles. And the claim, so the random permutations.
Anton,
yeah.
Some rather strange things here. What do you mean by when theta k are constants? The corresponding measure is called Evans measures. Is there any difference when?
So theta k depends on k, right? In my definition.
Yeah.
So if I replace the numerator by 1, then theta 1 would be equal to theta 2, would be equal to theta 3, and so on. Would not depend on k, would be just 1/2. It would be Evans measure with parameter 1/2.
Yeah, and but whether it's different from taking.
It's different from my measure. Because
it's different from your measure, but whether it's different from taking all thetas equal to 1.
Yes. Oh, yes, certainly. You see, if theta is good question, and let's discuss what happens if theta is equal to just 1/2, which is actually very close to our story. Then we associate this weight to a permutation, and when permutation, for example, has a single cycle of length n, we have just one factor 1/2. If it is decomposed in many factors, in many cycles, then we'll have 1/2 to the power number of cycles, which is much smaller, right? So for permutations, it's the weight would be the probability which would become much smaller. So we take with bigger probability, we take permutations which have small number of cycles, and with smaller probability, we take permutations which have large number of cycles. For example, permutations with many cycles of length 1 are really, we would rarely see them. So Evans measure, it really somehow it shifts the probability towards permutations which don't have many cycles. Do you agree? I'm ready to.
Yes, clear now. Yeah, thanks.
And however, so our probability is very close to Evans measure because zeta of 2k becomes very close to 1 very rapidly when k grows. So basically, you see the difference only for small values of k, and then it's the same. And the main theorem is that basically the probability distribution I was discussing for this number of cylinders or number of components, it's informally, it's basically indistinguishable from this probability distribution for random permutations when you tune it up in the way which was on the previous slide. And it's already the end of the lecture. I don't want to go into technical details, but of course, when you have a distribution, probability distribution, which ranges, grows, and becomes more and more. So all the probabilities become small. So you have to find some way how to compare different probability distributions like this. And there are different rates of convergence of one probability distribution to another. So informally, here the convergence is exceptionally fast and exceptionally well described. And the corresponding term in probability is mod Poisson convergence. And again, I don't want to go into details at the end of the lecture, but here, so on informal way, you take part of your distribution where basically all the mass is sitting, almost one. And for this part for large part of distribution, which contains your mean value and then sort of the interval, which is twice the variance or even more, and which indeed contains all the mass. The ratio of probabilities uniformly tends to 1 on all this huge interval. So that's the formula which is written in the slide. And to finish this story, I have to say that all these results, which are obtained with Delecruа, Gужар, and Zograf, they are based on two very important underlying results, namely on the volume asymptotics, on the asymptotic count of square tile surfaces during to Amal Agarwal, who proved that the asymptotics of Мэйзура-Вич volume is presented here. And by the way, so it was our conjecture. So now the similar conjectures about asymptotics of moduli spaces of abelian differentials and all individual strata already proved using mostly intersection theory. For quadratic differentials, the analogous conjecture for individual strata is still open. So we know conjectural value of these volumes of any stratum of quadratic differentials, and the asymptotic formula is very simple, but it is proved only for the principal strata. So this is still an open conjecture. And another keystone result which we use is this for asymptotic.
Sorry, Anton, will you please return to the previous slide? D should be a partition of G
of 4G minus 4 plus N.
Yeah, indeed. And what do you mean by Q of D1 Dn?
This is so. This is suppose for simplicity that N is equal to 0. To have one parameter, only G. So then sum of D's, so D's are partition of 4G minus 4.
Yeah.
The is that when G tends to infinity, the error term, so I can write that volume on the left equals this thing times 1 plus epsilon. And epsilon will become a function of partition. I claim that epsilon tends to 0 uniformly for all partitions when genus tends to infinity.
Okay.
And the similar statement for abelian differentials, where sum of D's is equal to 2G minus 2, is already proved. And I agree that it sounds very dubious. How can you get something uniformly well for all partitions? So it took to Martin Möller, I don't know, several years to convince Don Zagier that it's worth of even thinking of such a crazy conjecture. Here it happened to be true. And to my mind, this is like on the next slide. So this is the formula of Agarwal for approximation of intersection numbers. So we have intersection number on the left, and we have simple-minded expression and factorials on the right, where we hide everything in this factor which is 1 plus epsilon of d, where d is partition of 3g minus 3 plus m, right? So basically, the whole story is the story about what can be said about this epsilon of d. And the claim is that when n grows slower than g, when n is small o of square root of g, then uniformly for all partitions, we have uniformly well approximation. So this epsilon of d becomes uniformly, it's not epsilon of d, it's 1 plus epsilon. So epsilon of d, so you have to erase this one. It is the thing which is on the right. So epsilon of d becomes small. And the very last thing in this story is that...
Nope.
I apologize, this one is a misprint. It should be erased.
Mm-hmm. Yeah, and n is or small of the square root of g. Sorry.
So we have we have this Witten-Concevic correlator for mgn. And now g tends to infinity. I have to say something about n. You can either say that n is bounded or fixed, or you can even allow to n to grow, but not too fast. So for example, for all fixed n, it's even better. When n does not grow, then you have this error term, which is log g squared over g. Log g, it's almost constant, so basically we have an error term of the uniform error term of order 1 over g when n is bounded. Oops, the last conjecture is that if you take a billion square tile surfaces, the ones for which the holonomy of flat metric is trivial and which correspond to a billion differentials, then their distribution into maximal cylinders is described by usual random permutations. You do not need to twist this measure, just take uniform measure. And the very last comment in this connection is that there is one natural thing which I did not discuss. And what are the lengths of my cylinders? I discussed heights. What are the lengths? Or otherwise, you take a random geodesic multicurve. It has several components. What can be said about length of their components? The corresponding result will appear tomorrow or day after tomorrow in arXiv, and this is a work of Vансаном Делекруа and Min-Kung Liu, and they prove that the corresponding lengths satisfy Poisson process with parameter 1/2, and I don't want to spoil the pleasure of looking at their paper, but this is studied. And I think that I should not speak about train tracks. I think that there was already quite a lot of information. So if you want to get an idea of what are the coordinates in the space of multicurves, I suggest to read just one section of a book of Farber and Margoleti, Pryborn mapping class groups, where they consider the train tracks which live in a plane and which go around. So it's multicurves on a plane with 3 punctures, which is the same as 4-punctured sphere. And they describe train track coordinates there in an extremely accessible way. The book can be found on internet. I think that's all which I should tell today. I can tell this story in a rush, but I think that everybody's already tired.
Okay, thanks, Anton. Are there any questions, comments from the audience? No questions. Then thanks, and we'll meet in a week, I hope.
Thank you. Thanks a lot. Bye.
Да, спасибо, спасибо.
Вам спасибо за терпение.
It's a pleasure.
Но опять же, Антон, это, опять же, это, как сказать, можно только порадоваться за вас, но это, как это, красивая картинка и как бы понятные результаты, но совершенно непонятно, как можно в этом что-то достичь или разобраться. Он скорее, получается, что у тебя доклады такие, скорее рекламного характера, нежели математического.
Ну, согласен. Но ты знаешь, видишь, у меня ушло 1,5 часа на то, чтобы реально просто сформулировать результаты.
Это понятно. А вот ну, хоть какой-нибудь малюсенький кусочек, но такой, где бы можно было бы проследить все концы. Это сложно.
Значит, технически нет. А теперь, если ты хочешь, чтобы я рассказал про кишки...
Ну, то... не всего, но хоть какой-то маленький такой. Вот, то, с чего начинали, там, или какой-нибудь, не знаю, тор с одной точкой или что-нибудь в этом духе.
Да нет. На самом деле, как бы...
тор с одной точкой при жесте, стремящемся к бесконечности, да.
Как бы смысл такой. Смысл был примерно вот в этом... Сейчас. Вот здесь. Ну, замечательно. Мирзахани написал фантастические формулы, и все ответы есть. Что с ними делать теперь? Вот что делать с этими безумными таблицами чисел? И естественный вопрос, да, и это первое замечание. А второе замечание для нас – это подсчет поверхностей в клеточку. И есть разные подходы к подсчету объемов Мэйзура-Вича. Если смотреть на работы Эскина и Окунькова, то там даже непонятно, что объем положительный. Это глубоко не банальный результат, что объем положительный. В теории пересечений тоже нету никакой разбивки на объемы на куски. А здесь вот каждый из этих 6 классов дает какой-то вклад в объем, и все они положительны, строго положительны. И в этой ситуации очень естественный вопрос. Возьмем род большой, у нас очень много графов стабильных. На какие стабильные графы садится объем? Может так случиться, что они, условно говоря, все дают примерно одинаковый вклад, и это полная катастрофа. А может так случиться, что большая часть вымирает, а весь объем садится на несколько самых главных. Или вообще на один. Ну вот ответ, что объем садится на стабильные графы с одной вершиной и сколькими-то петлями. Причем число петель, которые, в принципе, когда у тебя есть одна вершина, число петель может быть от единицы до 3g-3. Про большое количество петель можно забыть. Число петель варьируется реально в районе логарифма g, и все. То есть из всех стабильных графов реальный вклад в объем приносит вот только стабильные графы, самые банальные, с одной вершиной и с небольшим количеством петель. Небольшим порядка логарифма. Это экспериментальное наблюдение, которое, в общем, можно было большой род можно было увидеть уже вроде 4 и уж тем более 5. Что вот эти вот стабильные графы с одной вершиной уже вносят почти весь вклад в объем, это видно уже вроде 4 и 5. И уж когда это было замечено, это было проверено для рода там, 10, скажем, но это стало очевидно. Дальше это нужно доказывать. Как это можно доказать? Если знаешь асимптотику всего объема и знаешь, что вклады стабильных графов с одной вершиной, они особенно простые. Ну, граф простой, понятно, что и вклад в некотором смысле он не хитрый. То, у тебя есть некоторые выражения через числа пересечения. Если доказать хорошую асимптотику для чисел пересечения, или хотя бы оценку снизу, Ты оцениваешь вклад вот этих самых простых стабильных графов, суммируешь и видишь, а у нас уже есть асимптотика для объема, и мы получаем уже все. И, сказать, наивно, это конец истории. А дальше начинается более тонкая часть. Почему о скорости сходимости распределения. И это несколько более технически более... Да, и почему это распределение сходится к распределению для случайных перестановок. Я должен сказать, что вот тут полностью принимаю претензии, потому что на данный момент ответ такой, потому что формулы так говорят. Я бы был бесконечно счастлив, если бы кто-нибудь придумал простое геометрическое объяснение, откуда здесь вылезают случайные перестановки, да еще с такой чумной мерой. Понятия не имею геометрически. Даже для поверхностей, забудем про то, что доказано, что не доказано, для поверхностей в клеточку, которые отвечают абелевым дифференциалам, таким, которые более простые, не нужно подкручивать меру, там получаются честные случайные перестановки с обычной равномерной мерой. Понятия не имею, почему. И, но это совсем недавние результаты, и нас с ними еще никто не поиграл. Здесь есть много с чем поиграть. Например, по ответам, если смотреть на вклады одноцилиндровых, двухцилиндровых и так далее, там, для поверхностей в клеточку, они вроде бы все интерпретируются через кратное зета-значение. Кратное зета-значение – это периоды. Периоды – это что-то геометрическое. Я не вижу, как... там, условно говоря, вот граничные классы какие-то. Но почему граничный класс видит распределение каких-то странных целых точек во всем страте и видит вклад в объем, понятия не имею. И так, навскидку, теория пересечения это ничего такого не говорит.
А там эти зета 2К по существу, если их чуть-чуть поменять, это будет уже неверно?
Это будет неверно. Точнее, вот как. У нас настолько точное приближение, что вот это вот очень точное приближение испортится. Мне пришлось по ходу дела учить вероятность, и, скажем, результат, который вот появится Делекруа и... я говорю по-русски, потому что я отвечаю на том языке. Уже можно говорить по-русски. Значит, как сказать? Вот если результат, например, что отнормировать и получится нормальное распределение, он, по-видимому, к этому будет нечувствителен, но он гораздо более грубый. То есть некоторые более грубые результаты этого не почувствуют, а тонкие результаты почувствуют.
Хорошо, понятно, да. Ладно, спасибо еще раз.
Спасибо.
Я в значительной мере принимаю претензии Максима, но, Максим, у нас статья еще только подана, даже не напечатана. Это все свежее, сырое, времени не было. А кроме того, нужно, чтобы люди с другими мозгами и с другой точкой зрения на это тоже посмотрели.
Сереж, Ландо,
Хорошо.
Да.
нам надо будет конференцию обсудить в какой-то момент.
Хорошо, давай завтра, там, послезавтра. Пиши, договоримся.
Ага.
Угу.
Ладно.
Спасибо всем.
Спасибо.
Всем. Пока.